Today we're going to continue our work from the last lesson and take a look at one of the biggest applications of equilibrium in general, LeChatelier's principle, which kind of looks at how equilibrium actually is, well, more dynamic than static. Instead of having our traditional do now where we reactivate what came before, I just want to kind of dive into it. So I'm going to play this video for you. It's only about 2 minutes long. I want you in your notes to just record any observations you make as we're watching things happen. Copper 2 chloride. I don't know why the video's doing that today. I'm good at cleaned up. You see on the bottom, with copper 2 chloride, the green powder. And that would be why it's green. No, you can't drink it. All right, so some things that we quickly observed. I don't know, I think we saw some color change. I saw that there was one container that had water, one container that had hydrochloric acid in it. That thing on the bottom was a stirring bar. It's a Teflon coated piece of metal, and then underneath the hot plate is another magnet. It's not another magnet, it's a magnet that spins on a motor, and then that will drag the metal bar with it, and then if it drags the metal bar, it'll end up stirring the solution. So it's a good way to keep things going. I imagine if you do this without the stir bar, you might actually be able to get a bit of a layer, like a green layer and a blue layer. I'm going to try that out tomorrow, and I'll upload another video if I get that to work out in person, because that would be interesting to see. But let's dive into this, because I saw some color change and I saw some chemical. So add more HCl. We saw that the blue solution turns green. And then if we had water, we were adding water to the green solution, so we saw that the green solution turned blue. So there's two big things I want to point out with this. The first is that the color changed at all, but that the color you saw the process happen. It started changing and then it finished changing. It changed a little bit when she poured in a little bit. I'm not quite sure who was doing the pouring. But the color change occurred. It was actually like in little steps. If you poured it in a little bit and a little bit and a little bit, we actually saw that happen in that stepwise process. So the key to understanding this is centered around something called complex ions. And as you can see, there's the definition there: an ion with a central metal ion bonded to more one molecules or ions on the outside. It's a coordination complex. The central ion is the coordination center, and the molecules around are called complexing agents or ligands. If I were to look at these ions look a little bit like something we've seen before in class. I'm going to draw it really quick. I'm really like locking onto the square brackets that we saw. This is what the carbonate ion looks like. And this is a polyatomic ion. And we remember that a polyatomic ion is ion means that it has a charge, and polyatomic means that we have covalent bonds. So it's this covalently bonded particle that overall has an electronic charge. And as you can see, we've got charges going on up here. And we've got these electrons getting into what looks like it might be a bond. There's an arrow present. And so that's good. That's a little bit confusing. But let me erase this all really quick so we get some room to write. And we can talk about what a complex ion is before we talk about the chemistry that was going on in the solution, because it's a complex ion that's being formed, and it's actually more like two complex ions. So a complex ion, group of atoms, which is just like your polyatomic ion, except now we've got a metal in the middle, sort of covalent, sort of ionic bond. I don't really want to get into the details of it, but here's what you need to know. These particles all do have their own octets on the outside, but this atom is actually donating 2 electrons into one of the empty spots in the metal in the middle. And the same thing happens with, you see, waters over here. It doesn't have to be an ion like a fluoride. A water has, basically anything that has lone pairs can donate into these positions. These particles that are connected are very transient. They can actually trade out with each other fairly easily. So what can happen is you can get your iron with these 6 waters, but one of these waters can pop out, and a different water with its lone pairs could substitute in. And so they can like trade out. So what we're showing down here is this is what the formula for your complex ion looks like. Note these square brackets. You can get a very entropically dynamic and complicated system showing up, which entropy-wise is a good thing. The other thing I should mention is complexes happen, like I said, with anything in the solution that has negative charges or lone pair electrons. So you could also get complexation showing up with the chlorides. And as it showed in the video, the compound that was dissolved in the water was copper 2 chloride. Is that there's a color component because these are transition metals. The biggest point I want to make about this solution here, the starting solution, is that that solution is not just blue. The better way to think about it is, since we know that complex ions can form, and we can do our research as to what complexes can exist, in a solution of copper 2 chloride, there's actually 2 different compounds present. There's a blue compound and a green compound. And so what we can kind of say, based on what we learned before, is that in this equilibrium, there is a ratio of green to blue. So over here, we would say that the green to blue ratio is much less than 1 because the solution's blue. There's so little green in there that you don't even really see it. And then in the solution on the right, I would say that this solution has a green to blue ratio that's greater than 1 because it looks green. And what we can see in the middle is, as we were adding the chloride, that the color was starting to change. There were some areas that were greener and some areas that were bluer, and if you let it sit, it would finish out and it would land at some color in the middle where maybe the green to blue ratio was 1 for a brief moment, but it was in transit from one ratio to another. And that is LeChatelier's principle. When a chemical system is at equilibrium, we, or nature, can impose a stress on it, change something. And when you change something, the equilibrium will behave in such a way that it bounces back. So we should say that equilibrium bounces back. Now, obviously, that stress in this case was a chemical that got added. And what we can see is that in the wording, the equilibrium position will shift. That's what I was showing here. By changing the value of the ratio of green to blue, you see a change in the actual equilibrium position of that ratio. This is a little bit confusing only because we are not looking at the whole chemical reaction. Remember before that we said that that ratio of products to reactants kind of always ended up being a constant? Well, that is true. But in this specific example, we're only looking at 2 of the compounds when there's really more compounds present. The bouncing back from a stress can also be viewed as undo the stress. So we're trying to like cancel out whatever the stress was. And by we, I mean the equilibrium, and the equilibrium isn't trying, it's just reacting, it's behaving. And we're going to look at how that happens. But perhaps we should probably look at a chemical equation first. So remember how I showed you all those complex ions? Well, copper makes two very useful for this demonstration complex ions. One is when you surround copper with waters, 6 of them fit. And as you can see, that complex has a blue color to it. And when you surround the copper with chloride ions, only 4 of them will fit, and that color is green. Well, based on conservation of matter, if copper is going to shed 6 waters and pick up 4 chlorides, well, we can actually write a balanced equation that shows that. And there it is. And going back to our images, I just want to make one more point. Even though the ratio here is a certain value and the solution is blue, because the solution isn't actively changing in color while it's sitting there, we can say at this situation on the left, it's at equilibrium. And then at the later situation on the right, it is also at equilibrium. It's the middle where we say we're not at equilibrium because we can actually see the color changing over time. That's the idea. If the color is changing, then the concentrations aren't constant. So it's this weird concept where we're in equilibrium and then we kind of get out of equilibrium and then we get back to equilibrium. So we should probably mention this about hydrochloric acid. I know I'm getting ahead of myself with my units, but when hydrochloric acid is dissolved in water, it actually introduces chloride ion to the solution. So when the stress is adding chloride, we said on the previous slide that the equilibrium will bounce back or try and undo the stress. So the goal is to reduce chloride. We want this number to come back down. And chemically, there's a conservation of matter. That's what this double arrow works the same way as a single arrow does, where we say, like, chemically this is equivalent to an equal sign, or yields, but we're not yielding, we're kind of going in 2 directions, so it's like yielding both ways. But in order to make the chloride ion go down, we kind of have to chemically bond it into a new substance. So the number one way I can make the chloride go down would be to make the forward reaction happen. I want copper with the waters to combine with the chlorides to make more of the copper chlorides. In fact, if I do this, now I will have less chloride afterward. Now the idea is we added some and it came back down, so I don't really want to fill in the chloride part. I kind of want to focus on everything else. If we're going to put some chlorides with some coppers to make this copper chloride, that's going to knock off a bunch of these waters. So I think the amount of free water should also increase. And by extension, conservation matter says if we're making more of the chloride-surrounded coppers, the amount of the water-surrounded coppers should go down. Because over the course of the whole video, we saw HCl added, we saw H2O added, but nothing changed the actual amount of copper that was in the beaker. So if we look at all the arrows we've drawn here, I think that the change in our products to reactants is going up. And that should be consistent with what we saw over here. If our product is green and our reactant is blue, we added chloride and it turned green. The ratio of green to blue went up so that there's more green and less blue. Now, if we were to follow that process the whole way through again with the water, if water gets added by us, the change that's observed is to reduce water. And this, again, is not talking about boiling off water. We're just talking about binding up the waters, trapping them so that they don't count as free waters. So if our goal there is to do that, we're going to want to surround the coppers with water, which would then consume the amount of the chloride-surrounded coppers. And again, if we're now surrounding our coppers with waters, we're going to have more free chloride. So we see on either side of this double arrow that that when we have this shift in equilibrium, it does look like that the products and the reactants all kind of do the same thing, as long as you're not focusing on the stress. As long as we only look at the things that aren't stresses, we can see that all of the reactants and all of the products will follow the same pattern, and in this case, we should see a decrease in our product to reactant ratio, as in more reactants and fewer products. So this is how equilibrium can shift, where you get more of one substance at the cost of another. And note, like, it does sound a little counterintuitive, like we're breaking conservation of matter, but don't forget that hidden in here is kind of an increase followed by a decrease, which is why I'm not really talking about what happens to the chloride when you add chloride. That seems circular. We saw graphs before, and I want to make them a little bit more complex, just a touch. When we have our balanced equilibrium down here between nitrogen and hydrogen to make ammonia, we see initially we're at equilibrium. We know we're at equilibrium because the concentrations are constant. I use these square brackets here. The use of square brackets is equivalent to molar concentration. Specific class, the specific time watching the video. You could see something written down where they say the Cl- concentration equals 0.1 molar. Right, so here we have constant concentrations. Here we have varying concentrations. And here we have constant concentrations again. Now what we can see is that we went from an equilibrium here, and then we've got a new equilibrium over here, as it says, but that new equilibrium does not look the same as the old equilibrium. They are constant, sure, but they're not constant at the same values of the original equilibrium. And that's how we get the shift. So we've got our stress. They tell you point blank what our stress is. And that stress causes the amount of nitrogen to increase. So that's our stress. In immediate response, we see an increase in the amount of ammonia and a decrease in the amount of hydrogen. And we actually see a slight decrease in the amount of nitrogen. To me, looking back at our reaction, I want to write out the reaction with some arrows that kind of help illuminate what's going on. So initially, if I've got a certain amount of N2 and I've got a certain amount of H2, and it's in equilibrium with NH3, we can kind of use the size of the arrow to communicate what's going on. So here we would say that the two arrows are probably roughly the same size. Here, they are the same size, roughly, forgive my art. But here, if we've got an actual change over time where the H2 is decreasing, the NH3 is increasing, the N2 is decreasing, well, if the H2 and the N2 are decreasing over time, that tells me that they're getting used up faster than they're getting replenished. So I would kind of say that in that middle zone, that the forward reaction is probably happening a lot faster than the reverse reaction, which does disagree with our definition. We said equilibrium means rates are equal. Well, after our stress, rates are temporarily unequal. Why are they unequal, though? Well, we increase the concentration of nitrogen. And we know that concentration can have an effect on rate. We learned that two lessons ago, where an increase in concentration increases the rate, but that's only for the reactants of a process. Reactants determine the rate, right? When N2 and H2 need to react, the amount of NH3 that's present doesn't affect how easily the N2 and H2 react. The only things that impact how N2 and H2 react are N2 and H2. So what happens is this increase in nitrogen will cause stress makes rate forward greater than rate reverse. While that's happening, you're decreasing in response, you're decreasing your nitrogen and your hydrogen. If that starts to happen, that means that the forward reaction will then, because as soon as you start using up your reactant, it'll start to slow down again. And then as soon as you start making more NH3, it starts to speed up again. And so what ends up happening is I feel like they're gonna meet in the middle. It's just that they'll meet in a new middle than they were at before. And so if we were to look at a graph of the rates changing over time, this would be a good example of how the rates looked in this initial equilibrium. This would be a good example of how they look in the new equilibrium. And you can see that the spike in the N2 causes a vast increase in the rate of the forward reaction, but then it immediately starts to slow down because you're consuming more reactant more quickly. The reverse reaction will then slowly start to speed up because you're creating more product more quickly, and then it kind of catches up. And so what ends up happening is you can see that the response in the N2 is actually to end up higher than you started, but lower than that peak. And that's how this whole equilibrium thing works. There's a stress, the response is to pull it back, but it never pulls it back to or beyond the point where you were first at equilibrium. It just never happens. This fits into what we were talking about before with the equilibrium position. We'd said where an equilibrium position where there's more products would be a product-favored equilibrium in general, but you can also have product-favored shifts. One last thing I wanted to look at before we wrap things up was I found this interesting video of cobalt ions. Again, now that we know the reaction, this should probably help things. Oh, I'm going to have to fix this slide. This slide is wrong because that's not the stress. So what they're going to do is the title here kind of gives it away, but they're going to add silver ions to a cobalt complex, and there's no silver in the equation, so we're going to have to pick that apart. But before I pick it apart, I just want to let you watch. I think it starts around
forward direction. We'll start with two test tubes with the cobalt water complex ion. We add 12 molar hydrochloric acid to one of the two.
12 molar.
We notice that the solution turns blue. This indicates that the equilibrium has shifted in the reverse.
Oh, actually, no, that's kind of good. I like that. I want to close that. I like looking at this really quick, just to interrupt. You can actually see here when you don't mix, you actually get like a gradation. You can get like a blue section and a pink section. If you let that sit long enough, I'm sure that, you know, entropy takes over and then the particles will be evenly mixed. But you almost prefer to get that barrier because it looks more interesting.
Direction. The hydrochloric acid provides a source of chloride ion. As we increase the concentration of the product, the equilibrium shifts in the reverse direction to use up the added chloride ion. We will now add some silver nitrate solution to the cobalt chloride complex ion. We notice the formation of a white solid, which is...
Now we should know what this white solid is, given what's here. I mean, we're going to write down the silver. If we're looking at what silver... I'm going to fix that parenthesis. It's probably sticking out to some of you. I can color that in. There you go. This silver ion is clearly combining with something to make a precipitate. So looking at what I have in my solution, I only see one substance that actually will create a precipitate. Precipitate being an ionic compound. So this is a cation. We're going to need an anion. I think this is our anion. So what's going to happen is this plus the chloride is going to make, and that to me looks pretty one way. Now we know in a saturated solution, which I would imagine this is because we see some solid, we're going to see an equilibrium established. But even so, as you establish a new equilibrium, this new equilibrium will bind up some of our chlorides.
The silver chloride. We also notice that the solution is turned from blue to pink.
Well, then we can probably explain what's going on. I don't think this is our stress at all. What stress would the addition of silver make? And then also we can make sense of that. What color does it turn? And we can kind of answer this from the other direction. Let's approach this from the other direction. He said it in the video, and I'll include the link if you want to watch the whole thing. He said the reaction turned pink. That means we know what happened to the shift. We know that the shift here is going to be shift left, reactants. The change in the ratio will be down, which means we can kind of fill in everything. Now, I think since the silver interacts with the chloride, we're not going to worry about that. But if it's a shift left, this has to be what happened, because that's the same shift left we saw on the previous slide, a reactant favored shift. Which means, well, what has to have happened here is the response has to match up in the chloride, has to match up with what happened to the cobalt. So the change is we have to increase the chloride ion, which means that the stress had to be a decrease of chloride ion. The chloride ion that was in the solution when it was blue got trapped in silver chloride, which reduces the amount of free chloride, which means that the equilibrium will be observed to try and free up some more chloride to take its place. So you can actually stress an equilibrium by a decrease as well. So to sum things up, so far we've talked about stressing an equilibrium, which I did see this answer in a lot of your packets from today. The stress of an equilibrium can be made by increasing, decrease, in each case, observed, response. So if we're going to increase if the stress is increasing the reactant, the observed change is going to be a shift towards the products so that we reduce reactants. If you decrease a reactant, the observed response is a shift towards the reactants to fill the void, to replace the reactants, which would decrease the products. An increase in the products would mean that we'd see a shift towards reactants, and a decrease in the products would be a shift towards the products. And so I guess the best way to sum this up is, at least in terms of concentration, the shifts are away from an increase, if we're going to say that, in our generic reactants are in equilibrium with products. An increase in reactant will cause a shift away from the increase, an increase in products away from the increase, and towards a decrease. So when I say away from an increase, I'm talking about a shift in the equilibrium position, the ratio. Hope this helps. I'm going to link all the videos that we saw in this presentation in the description, and thanks for watching.